Ever wonder how massive apps like Netflix or Spotify just work so seamlessly? Well, a huge part of that magic comes down to this really cool idea called containers. So today we're going to break down what they are, why they're such a big deal, and how they solve one of the most classic, most frustrating problems in the entire world of software.
All right, let's get into it.
Ah, yes. If you've ever worked in tech, or even just been near a developer, you have definitely heard this phrase. It's that classic hair-pulling moment, right? An app works perfectly for the person building it, but the second it moves to a different computer, it just completely blows up. This one sentence, this one single frustration, is the entire reason containers were invented. So to really appreciate the genius behind containers, we have to travel back in time a little bit. We need to understand the world before they existed. And let me tell you, it was a world filled with chaos, weird inconsistencies, and just painfully slow processes.
And you know, what's funny is how all these problems were connected. It was a domino effect. You'd have these crazy conflicts because, say, your laptop had version 1 of a library, but the server had version 2. The old school fix for this was something called a virtual machine, but they were monstrous, huge, slow, and they ate up all your computer's resources. All this meant that no two environments were ever exactly the same, which made trying to grow your application an absolute nightmare. It was just a constant uphill battle. And this is where containers step onto the stage. They offered a totally different approach, a fundamentally better, smarter, and way more efficient way to package and run software that just cuts right through all that chaos we were just talking about. Let's really chew on this definition for a second, because the key words here are everything. Lightweight. That means they're small and super fast. Portable. That means you can pick one up and move it literally anywhere, from your laptop to a server in a closet to the cloud, and it just works. And consistent. That's the magic word. That's the word that finally solves the "it works on my machine" problem once and for all. Because everything the app could possibly need is already packed inside.
You know, the best way to think about a container is as a perfectly sealed, totally self-sufficient box. Inside this box, you put your application, but you also put all of its friends, every specific thing it needs to run, the exact right versions of its libraries, its tools, its configurations, the whole shebang. And once that box is sealed, it doesn't matter where you ship it. The contents inside will always behave in the exact same way.
And this table right here, this shows you why they are such a leap forward. A virtual machine, the old way, had to pretend to be an entire computer. That meant it needed its own complete copy of an operating system. That's why they were massive, measured in gigabytes, and took minutes to start up. Containers, on the other hand, are so much more clever. They just share the core operating system of the computer they're running on. This little trick makes them incredibly small. We're talking megabytes, and they can start up in seconds. It's a huge difference. So how is that even possible? How can a container feel like its own private little island, its own little machine, without actually being one? Well, it's not actually magic, but it's close. Let's peek inside that sealed box and see how it really works. The secret sauce really boils down to 3 brilliant features that are built right into the Linux operating system. Now don't worry, we're not going to get super technical here, but if you can wrap your head around these 3 concepts, you'll totally get how containers work their magic. Okay, first up, namespaces. This is the feature that creates the powerful illusion of being alone. Basically, a container is given its own private set of namespaces, which tricks it. It thinks it has its own exclusive set of processes, its own private network, its own pristine file system. From inside that container, it genuinely looks and feels like it's the only thing running on the entire computer.
Next, we've got control groups, or C groups for short. So if namespaces create the isolated room, C groups are the guardrails inside that room. They let you be really specific and set strict limits on how much of the computer's power, the CPU, the memory, the network, a single container is allowed to use. This is absolutely critical because it means one badly behaved container can't get greedy and crash the whole system. And the final piece of this puzzle is the union file system. This is what makes containers so incredibly efficient. See, instead of being one giant clunky file, container images are built in layers, kind of like a cake. You might have a base layer for the operating system, then another layer for the programming language, and then a thin layer on top with your actual app code. These layers can be reused and shared, which makes building, downloading, and updating containers unbelievably fast.
So this brings up a really crucial point. We have to understand the difference between an image and a container. Think of it this way. The image is the static, read-only blueprint. It's the recipe. It's the instructions for our sealed box.
A container, on the other hand, is a live running instance of that image. It's the box in action. You can use one image, one blueprint, to create hundreds or thousands of identical running containers.
Okay, that's enough theory. Let's see how this all snaps together in the real world. We'll start by looking at the actual recipe for building one of these containers.
This right here is called a Docker file. It's basically a step-by-step recipe for building a container image. It's really simple. Step 1, we say from node 18. That means we're starting with a base layer that someone else already made, one that has Node.js version 18 installed. Then we just make a new folder inside our container to hold our app.
Next, just like a recipe, we start adding our ingredients. We copy in the file that lists everything our app depends on, and then we tell the container to install all of it. And remember, this is all happening inside that clean, isolated environment of the image we're building.
And for the final step, we copy in our actual application code. And then, this is the most important part. We tell the container exactly what command it should run the moment it starts up. And that's it. That's the entire recipe. We now have a complete, totally self-contained blueprint for our application.
Now, let's take that simple idea and scale it way up, because this is where containers really truly shine. In modern software, a big application is often broken down into a bunch of smaller, independent services called microservices. And as you can see here, each service can be written in a completely different language. You can have Java talking to Node.js talking to Python, and it doesn't matter, because each one lives happily in its own perfect isolated container. The payoff for doing this is just immense. Your team can update the payment service without ever having to touch or worry about the user service. If suddenly everyone wants to see your products, you can scale up just that one piece of the system. You get the freedom to use the best tool for the job every single time. And maybe best of all, if one service has a problem and crashes, it doesn't take the whole application down with it. It's a total game changer for building big, reliable systems.
So let's just zoom out for a second and appreciate the massive impact that containers have had on, well, pretty much everything in modern software.
So to quickly recap the greatest hits, they are incredibly fast and use resources way more efficiently. They guarantee consistency from a developer's laptop all the way to production. They slot perfectly into all the modern automated workflows we use today. And really, they are the fundamental building block of the entire cloud-native world.
But you know, it's important to be real about this. Containers aren't a magic wand that fixes everything. Because they share that host operating system, their isolation is technically a little weaker than a full-blown virtual machine. That also means you have to run Linux containers on a Linux machine. And other stuff, like managing data that needs to stick around, or making sure everything is locked down securely. That takes some careful planning.
And that brings us to the final, really important piece of this whole puzzle. Look, if you have 10 containers, you can probably manage them by hand. But what happens when you have 10,000? That's where a system like Kubernetes comes in. You can think of it like this. Containers are the standardized Lego bricks, and Kubernetes is the master builder that knows how to arrange them, scale them, and even fix them automatically when they break. Which leaves us with one final thought. We've established that containers are the fundamental building blocks for modern software. But a pile of blocks is, well, it's just a pile. To build something truly incredible, something resilient and powerful, you need a plan. You need a manager. So if the containers are the blocks, who, or maybe what, is the architect?